Hi everyone, welcome to this section on regression analysis. So this is our first section on supervised machine learning. So in this section, we are going to cover a lot of topics. So this is the list of topics which we are going to cover in this section. So there are quite a few topics and we also have quite a few number of projects in this section. So we will start by discussing what is the origin of the regression. So in this topic, we will start from the concept of a straight line and then we will reach to the concept of regression. Then we will study what is the definition of a regression and what we require from the regression. So basically from the regression, the requirement is to use the given set of feature and to predict the continuous output value. Then we will study simple linear regression. In simple linear regression, we usually use the simple data sets, that is a data set with only one features. Then we will study multiple linear regression. In multiple linear regression, we have more than one features in our data set. Then we will study least square regression. Basically, least square is the method which we apply on the regression in order to reduce the error. So during the prediction, if we get errors from the regression model, we want to reduce these error. So we will apply least square method to reduce the error and to find the optimal value of the weights for the regression model. Then we will also study regression by the gradient descent. Gradient descent is also an algorithm to reduce the error and to find the optimal value of the weights. Then we will study polynomial regression. Now in polynomial regression, we will try to fit a curve other than a straight line on our data set. Usually we want to fit a straight line. In regression modeling, we want to fit a straight line on our data set, but in polynomial regression, we try other than a straight line and we try a curve or some sort of a sinusoidal wave to fit our training data set. So this is the polynomial regression. Then we will learn about the cross validation. So cross validation is an important technique of splitting the data into a training and testing component. Then we will learn about the bias variance trade-off. So high bias model and high variance model is not desirable. So what we do in order to accept one value, that is in order to accept the low value of a bias, we can compromise on the value of the variance. Or in other words, we can see that in order to get or in order to accept the low value of the variance, we compromise on the value of bias of the model. So we cannot get both best value for the model. So we have to compromise on one of the value while selecting the other. So that is called bias variance trade-off. Then we will learn about the underfit and overfit model. We will see the underfit and overfit models are also non-desirable because the underfit model is not performed well either on a training data or on a test data. So underfit model performed bad on both training and testing component of the data. In overfitting, the model learns the noise of the dataset. It may perform well on the training, but its performance on unseen dataset is poor when it is overfitted. Then we will study three kinds of regularization. So they are known as ridge regression or L2 regularization, then a lasso regression or L1 regularization, then we have elastic net regularization. So basically, these are the three important terms of a regularization. So regularization is a technique in order to avoid overfitting, because overfitting is undesirable where model learn the noise of a dataset and also it doesn't perform well on the testing component of the data. So in order to avoid overfitting, we will study these three kind of regularization and we will apply these regularization to our regression model in order to avoid overfitting. Finally, we have 9 projects in this section. So what we will do in these 9 projects? So basically in these 9 projects, we will implement all these topics in Python and we will see how to implement simple linear regression in Python, multiple linear regression, least square method, gradient descent, polynomial regression, how to implement cross validation and how to implement ridge regression, lasso regression, and elastic net regularization. So basically in these 9 projects, we will learn about all these topics and we will see how we can implement these topics in Python. So I hope you understood this lecture. I hope you are waiting to enter into the section. This is going to be a very exciting section for you and you will learn a lot from this section. Thanks for listening. I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will see about the origin of regression. We will discuss from where the concept of regression arises. So the concept of regression arises from the concept of a straight line. That's why regression is not a very new topic in machine learning. So this is the slope intercept form of line from our high school mathematics. We know that the slope intercept form of line is represented by this equation, which is y is equals to mx plus b, where m is the slope of a line and b is called the y-intercept, or it is the value of y when x is equals to 0. Now let's discuss this slope-intercept form of line in detail. Now this is my data set. Now this data set is very simple as it has only 4 samples, 1, 2, 3, and 4. It has 2 variables, x and y. The x variable is called input variable or independent variable, whereas the y variable is called output or dependent variable. If I want to draw a straight line or I want to plot a straight line from these 2 variables, I can easily do that. So when x is equals to 0, y is equals to 2. And similarly, when x is equals to 1, y is equals to 4. So by connecting these points, I can easily draw a straight line which is shown here. So this straight line is a representative of this small data set where x and y are 2 variables. Now it's time to find 2 another important elements, which are the slope and the intercept. So how to find the slope and how to find the intercept? First, we will find the intercept because it is more easy. If we see here, this is the definition of the y-intercept or definition of b. So b is y-intercept, or it is a value of y when x is equals to 0. So from this data, we can see that when x is equals to 0, y is equals to 2. It means 2 is the value of b, or 2 is the value of intercept here. Here it is denoted by b, or this is called the y-intercept. So we can see that we have easily found out the value of b, which is the value of intercept. Now it's time to find the value of m, which is the slope. Now slope is defined as the change of y with respect to x, the change of variable y with respect to x. So in this way, with the help of this table, we can also find the value of slope easily. So in order to find the change in y, I have to use any 2 consecutive value of y. I can use 2 and 4. I can use 4 and 6. I can use 6 and 8. So let we use last 2 value of y. So if I subtract 6 from 8 in order to find the change of y, and then 2 from 3 in order to change in x, in that case, the ratio will give me a value of 2. Now, slope is also 2. The intercept was also 2. Now, if I put these values here, I will get the equation of a straight line. So this is the slope intercept form of a line, which is also a basis about the concept of a regression. That's why we are starting from here. Let's transform this knowledge of slope intercept form of line into some real data set. So again, here I am taking a real data set, which is very small. That is, it is also it has only 5 samples, 1, 2, 3, 4, and 5. Now it has only 2 variables again, and one variable is experience in year, the other variable is salary in dollar. So experience in year is the independent variable, whereas salary in dollar is dependent variable, because salary is dependent on the experience. So if the experience is 0 year, the salary will be $20,000. It means if the candidate is a fresh graduate and it doesn't has any experience, its salary will start from $20,000. If the experience is of 1 year, then its salary will start from $40,000. Similarly, if the experience in year is 4, then the salary will be $100,000. So if I want to plot a scatter plot out of this data, so I have 5 points to plot. So this is my point 1, 2, 3, 4, and here is my point 5. So we can see that when experience is 0, the salary in dollar is 20,000. So we can see here, when experience is 0, the salary is 20. When experience is 1, the salary is 40. When experience is 2, the salary is 60, and so on. So these are the scatter points, and this is called the scatter plot of this data set, where we have plotted salary against the experience. That is, we have plotted dependent quantity against the independent quantity. Now, let's draw a line to connect these points. Now, this is a very important slide, and there are a lot of information which I have to discuss with you about this slide. So the first important point is that we have connected these dots or these data points with a straight line. When we connect these data points with a straight line, now it is not only a straight line, it is our linear model. When we say linear model, basically by drawing a straight line, we have trained a linear model on these points. How it has been trained and what it has learned and how it will benefit us. So we have to discuss all this in this slide. So basically, if I go back to the previous slide, I had only 5 data points. So this is called the scatter plot of these data points. When I join these data points with a straight line here, so basically this is not only a straight line, but it is also a linear model. By drawing a straight line on these points, basically I have trained a linear model. Now this linear model is trained and now it is going to benefit us. Now discuss a few more things before we see how it is trained and how it is going to benefit us. Now here X is experience is air or it is an independent variable. The salary in dollar is our dependent variable for this example. Now the slope is 20,000 and intercept is also 20,000. You can see the intercept is the salary value when the experience is 0 or when the X value or when the independent variable is 0. So you can confirm from here, this is our intercept. Similarly, you can easily find the slope by taking the 2 consecutive Y quantity and the X quantity. So the slope is also 20,000. Now I want to convert this equation of slope intercept form of line with respect to this real salary data set. Now Y is salary, M is my slope, X is the experience, and B is intercept. So we have transformed this data set into a new equation with the help of slope intercept form of a line. Now, again, the important thing is if you see this straight line as a mathematics student, this is only a straight line. But if you are looking this line as a machine learning practitioner, so this is not only a straight line, but it is a linear model which has learned something. So what it has learned? It has learned the relationship between X and Y. That is the relationship between the independent variable and the dependent variable. How it has learned the relationship? Basically, it has learned that when the experience is 0, salary is 20,000. And when the experience is 4 years, the salary is 100,000. And it also has learned all the values between them. So by drawing a straight line on the data points, it means you have trained a model and it has learned a linear relationship between the independent variable and dependent variable. Now, this straight line is also known as our linear model. So here is the straight line. Now, this is not only a straight line, it is a linear model because it has learned a linear relationship between the independent variable and the dependent variable. Now, what is the proof that it has learned something? Now, it has learned, now it is going to benefit us. Suppose a candidate comes to us whose experience is only 1.5 years. Now, this value 1.5 is not present originally in our data set. But since we have trained a model on this data set, now this model, which is a straight line and which is also known as linear model, will help us to find the salary of a person whose experience is 1.5 and this value is not present originally in the data set. So now this is the testing point for this linear model. Now I am supplying 1.5 year to the model here, and here model is giving me the prediction. So model is telling that if the experience of a candidate is 1.5 year, its salary should be 50,000. Similarly, if another candidate comes to us whose experience is 3.5 years, now this model will help us to find the salary of that candidate. Although this 3.5 is not present in the training data, but since this model has learned the linear relationship between the independent and dependent variable, or between the experience in years and salary in dollars. Now it is going to find the value of salary for any experience in years. So if a candidate comes to us whose experience is 3.5, so I will give this input to my model. So this is my testing point. So when I will give this input, it is giving me the prediction. So we can see that it is suggesting that the salary of the candidate whose experience is 3.5 years should be equals to $90,000. So in this way, we have seen that this is our linear model, and it has learned a linear relationship between the X value or the independent variable and the Y value or the dependent variable. So this is the definition of a linear model. So the linear model establishes a linear relationship between a dependent variable and an independent variable. So this model has learned a lot about the experience in year and salary in dollar. If a person comes whose experience is 10 years, even then we will be able to find its salary with the help of this linear model. In that case, since we know the slope of this linear model, we will extend this linear model further to a value where it reaches to a point where the experience is 10 years. And in that case, we will be able to find the salary of a person. So student, in this way, we have learned that a straight line which is connecting the points is not only a straight line, but it is a simple linear model which has learned the relationship between the X quantity, that is independent variable, and the Y quantity, which is the dependent variable. After training this straight line model or a linear model, we can take help from this model by giving any input, so it will be able to predict the output. So this model has established a linear relationship between a dependent variable and an independent variable. So till now, we have learned this. We have trained our linear model on a training data. We have X, we have Y, and we have trained our linear model on this data. So after training, when we give a new sample to this linear model, which is not present in our training data, that is when we pass a test sample to our trained linear model, it is able to give us the prediction. So in this lecture, we learn about the origin of the regression. We see that the origin of the regression comes from the concept of a straight line, and the concept of the straight line basically gives the concept of a linear model. A straight line is not only a straight line, it is a linear model which establishes a relationship between a dependent and independent variable. And it learns this relationship, and after learning, this straight line is able to help us to give the output with respect to any input value. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will discuss the definition and the concept of linear regression. Since we have learned about the linear model, now it's time to transform the knowledge of linear model into the concept of linear regression. So this is the definition of a linear regression. So linear regression is a process where there exists a linear relationship between the independent variable and dependent variable. So this is the equation which is defining the concept of a linear regression. This equation is saying that y is the function of x, or y is dependent on x, or the dependent variable is dependent on independent variable, or y is dependent linearly on the independent variable. So this is the simplest equation which governs the idea of a linear regression. So the concept of linear regression is almost the same as that of a linear model, because a linear regression in its simplest form is just a linear model. Now here x and y are also known as features and target. So in linear model, we called x as independent variable and y as dependent variable. But in linear regression, we will call them as a feature and target. So the concept is saying that is the target depends upon the feature. Targets are dependent quantities and features are independent quantities. Now it's time to transform our linear model equation into the standard regression equation. So that is our linear model equation. Here I am written as salary is a dependent quantity and experience in air is an independent quantity. Therefore, salary is a function of experience. Now, this is my basic equation of a line, or this is called the equation of a linear model. Now, when I transform this equation of a linear model into a standard regression equation, I have to replace few variable with the new variables. The concept is same. So first I am replacing slope with W and intercept with W naught. So if I replace slope with W and intercept B with W naught, so this is my new form of equation. So it is Wx plus W naught. So if I write W naught first and Wx after, then this is called the simplest form of regression or the standard regression equation, where W naught is now known as bias. We will not call it intercept. Now it is called as bias when we will study in the regression. The concept is same. And W is called as the weight which is associated with X. So X is our feature. This X is our feature. Y is our target. This is a bias and this is a weight. So we have to remember these terms in order to progress further. Now, in this lecture, we have transformed the concept of a linear model into a concept of linear regression. Similarly, we have transformed a linear model equation into a standard regression equation. So this equation, which is a standard regression equation, is very similar to a linear equation, except there is a change in the variable notation. Now we are using a W naught and W instead of B and M. Now W naught will be called as a bias of a regression model and W will be called as a weight which is associated with feature. So we will discuss both the concept of bias and weight detail in the coming slide. So I hope you understood this lecture. Thanks for listening and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn that what we require from the linear regression model. So if we recall from the previous lecture, that in previous lecture, we learned the basic definition of a linear regression, that linear regression is a process in which we establish a linear relationship between the independent variable and dependent variable. We also learn how to transform the equation of a linear model into standard regression equation. Now we have standard regression equation. Now what we require from the regression model. So in order to understand the requirement from the regression model, let's see this salary data set. So this is the salary data set and this is the scatter plot of the salary data set. If I want to train a model on this salary data set or on this training point, I have to connect this point with a straight line. So this is my linear model or a regression model, which is trained on these data points. Now this model has trained, this regression model has trained. What is my requirement from this model? So my requirement from this model is that if I give a new test sample to this model should be able to predict the salary or the output value. So it means if I give the input or a new test sample as 1.5, so it should be able to give the salary of a person whose experience is 1.5. Similarly, if I give a new test sample of 3.5 year to this model, it should be able to predict the salary of a person whose experience is 3.5 years. So the requirement from the regression model is that after training, it should be able to predict the dependent quantity if a new independent quantity or if a new value of an independent quantity is given to the model. Now, this is another example. This is a dataset known as housing price dataset. In this dataset, the price of a house depends upon the area of a house. So the value for the area of the house are 200, 300, 400, and up to 1000 square meter. So if we train a regression model on this dataset, so after training, our requirement from the regression model should be that it should be able to predict the price of a house if a new value of the area of house is given. So here the values are 200, 300, and 400. So if I give a value of 580 square meter, now 580 square meter is not present in the data set, but since the regression model has trained, so our requirement is that that model should be able to predict the price of a house whose square area is 580. That is, our requirement from regression model is to predict the price of the house if the area of the house is 580 square meter. So the requirement from the regression model is very simple. The requirement is prediction, whether to predict the salary of a person or to predict the price of a house. So after learning, the regression model should be able to predict the value if a new test sample is given to it. So in this lecture, we learn that what we require from the regression model. I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will learn about the simple linear regression. So a linear regression becomes a simple linear regression if we perform regression on a single feature. That is, if we have a data set where the output quantity or a dependent quantity depends upon only a single feature, in that case, the regression will be known as simple linear regression. So here is the example of simple linear regression. So this is our salary data set. In our salary dataset, we have only one feature, which is experience in year, and we have target values. So the target depends upon only one feature or a single feature. In that case, if we perform regression on this simple dataset, which has only one feature, our regression will be known as simple linear regression. So this is the equation of a simple linear regression. We can see that there is only one weight in this equation because we have only one feature, which is x. So this is the definition, or this is the equation of simple linear regression, where our y quantity or target depends upon only a single feature, that is only one feature, which is experience in year for this salary data set. Now there are two important cases in simple linear regression. So this is case one. There is a situation when bias will be 0. Suppose this is our data set where we are measuring the speed of a car with respect to time. So when time is equal to 0, the car is at rest and its speed is also 0. It means here there is no bias. That is, the value of y is also 0 when x is equal to 0. Now, when the time is 1 second, then the speed is 2. When time is 2 seconds, then the speed is 4. In a similar way, when the value of time is 4 seconds, the speed becomes 8. So if I plot this data set, I will get a straight line which start from the origin, that is where x value is also 0 and y value is also 0. So if I put this information in my simple linear regression equation, so this is my equation. Here the bias is equals to 0. And if I put bias is equals to 0, then I will get y is equals to wx, and this w is 2 here. Now, how w is 2 here? Basically, the concept of w is same as the concept of a slope. If I want to calculate the slope from this dataset, which is equal to the weight of the simple linear regression, I will get the value equals to 2. So if I put this w equals to 2 here, I will get y is equals to 2x. Now here comes the first concept of a weight. So here weight is equals to 2, due to which our equation becomes y is equals to 2x. So the first concept of a weight is that weight is the quantity which establishes a linear relationship between the independent variable x and the dependent variable y. So we can see that the first concept of a weight is that weight is important in order to develop a linear relationship between x and y. If weight is equals to 0, then there is no concept of a linear modeling, because there will be no concept or no relationship between the x quantity and the y quantity. So that was the first case about the simple linear regression, that if the bias of a data set is 0, then the equation becomes y is equals to 2x for this particular data set. And here we are able to extract the information about the weight. The value of weight is equals to 2, and the concept of the weight is that it is the quantity which establish a relationship between y and x. Because when x is equals to 0, then y is also 0. When x is equals to 1, then y is equals to 2 times of 1, which is 2. So we can see that when x is equals to 1, y is equals to 2. When x is equals to 2, y is equals to 4. So with the value of weight is equals to 2, we are able to find the linear relationship between x and y. So this is case 2 about the simple linear regression. There is a possibility when weight is 0. So what will happen in that case? In that case, if you see this data set, the y quantity does not depend upon the x quantity. Whatever be the value of x, y is constant, which is equals to 2. In that case, what is happening? That the y quantity is independent of the x quantity. In that case, we will get a straight line like this, whose slope is 0 or whose weight is equals to 0. The value of intercept for this particular data set is 2. So if I put the value of intercept is equals to 2, or value of bias is equals to 2 here, and the value of weight is equals to here, I will get y is equals to 2. Now y is equals to 2 does not tell us anything about the relation between the independent variable, which is x, and the dependent variable, which is y. So if weight is equals to 0, we cannot establish a relationship between x and y. That's why the first concept of the weight is that weight is the quantity which establishes a relationship between y and x. And when weight is 0, there is no concept of a linear modeling. There is no linear relationship between x and y. So in this lecture, we learn about the basic definition of simple linear regression. We learn that if we have only one feature in our dataset, and if we perform regression on such kind of dataset, then that regression is called simple linear regression. Since in simple linear regression, we have only one feature, therefore we have only one weight. Then we discuss two important cases, that when bias is equals to 0, what will happen to the equation of simple linear regression, and when weight is equals to 0, what will happen to the equation of simple linear equation. So we learn a very important concept about the weight, that is, weight is the quantity which establishes a linear relationship between x and y. If there is no weight, there is no concept of linear modeling, and there is also no concept of linear regression. I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this lecture is all about the concept of multiple linear regression. So linear regression becomes multiple linear regression if our target value depends upon more than one feature. In the previous lecture, we studied that if our target value depends upon only one feature, so that regression is called simple linear regression. So in multiple regression, our target value will depend upon more than one feature. So this is the example of multiple linear regression. This is our salary data set, and here I have added an additional feature, which is years of education. Now this feature is denoted by x2 in this data set. Now I have two features, x1 and x2, and my target variable, which is salary in dollar, depends upon these two features. In that case, my regression will be known as multiple linear regression. If you see this equation, this is the equation of multiple linear regression, where we have two features, x1 and x2. Now you can see that every feature has its associated weight. So w1 is the weight associated with x1, and w2 is the weight associated with x2. Now the value of weight will decide which feature is more important. The thing is, when we have more than one features, then it is not necessary that all features are equally important. It is the value of weight which decide which feature is more important. So in this way, suppose if W1 is 5 and W2 is 10, it means the weight associated with second feature has the largest value. It means this feature will have more influence on Y as compared to X1. So the value of weight decides the influence of a feature on the target variable. So this is the example of multiple linear regression. And now your salary doesn't depend only on the experience in year, but also the years of education, that whether you have received a 16 years of education or the 18 years of education. Let's understand more about the multiple linear regression with an example. So this is an example of a peanut butter and a jelly sandwich. Now, how it is an example of a multiple linear regression? Basically, it has two features, that is peanut butter and a jelly. So these two features constitute the multiple linear regression problem. Suppose you have a restaurant and you are selling a peanut butter and a jelly sandwich. In that case, you have two features. Your first feature is peanut butter and your second feature is jelly. and W1 and W2 are the weight associated with those features. Now, what is the concept of weight in this particular example? So W1 is basically the amount of peanut butter which you are putting in your sandwich, and similarly W2 is the amount of a jelly. So if you put more jelly, that is if W2 is greater than W1, then the taste of sandwich is more towards the jelly. You will feel the jelly taste more as compared to peanut butter. So in this way, we can see that the weight controls the amount of the feature, or it controls the influence of the feature on the output. The output of your multiple linear regression in this particular example is your sandwich. So your sandwich depends upon two features, x1 and x2, and you can control these features with the value of weights W1 and W2. And here the concept of weight is the amount of peanut butter and amount of jelly you are putting on your sandwich. Now here again, there is another concept here, which is the concept of a bias here. So if your x1 is 0 and x2 is 0, it means you are not putting any peanut butter or a jelly on your sandwich. Even then, you can get a bread. So it means the bias is a quantity, or bias is a thing which will give you some output. Even then, you do not have any feature. So if all of your features are 0, or if the weights are 0, even then you can get something at your output. So in this example of a peanut butter and a jelly sandwich, we learn the concept of a multiple linear regression. We see that if we have more than one feature, we will definitely have more than one weight. So the value of the weight will decide which feature has more influence on the target value. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So this lecture is all about target values and the predicted values. So the target values are those values which are provided in the dataset. So these are our target values for a salary dataset, and this is the feature of our dataset. So if I plot a scatter plot out of this salary dataset, I will get those 5 points. So these are called the target values, and these are the values on which I will train my regression model. After training, the regression model will give us the value, and that value will be known as the predicted value. So let's see how we can get the predicted value from a model. So here I am connecting these target values or these target points with the help of a straight line. Now we know that this is not only a straight line, this is a linear model, or this is a linear regression model having only one feature. So this is our target value, and when we draw a line on these target value, this is our linear model. So the values predicted by this linear model will be known as the predicted values. So the case where the target values and the predicted values are same, that will be considered as an ideal situation. And in the ideal situation, there will be no error and the accuracy of model will be 100%. So this is the ideal scenario in which all the predicted values are equal to the target values. But here is the real situation. In the real situation, we can see that all the predicted values are not equal to the target values. So these green dots are our target values, and this straight line is providing us the predicted value. We can see that for this data set and for few of the data set, the target and the predicted values are same. But some of the points or some of the targets are away from the predicted value. In that case, we have to calculate the error. So in a real situation, whenever we have to perform a linear regression, we have to calculate the error, because in that regression, the target values are not always equal to the predicted values. So in that case, we need to calculate the error. So this is the concept of an error with the help of a picture. So this is the pictorial interpretation of an error. So if this is our target value and this is our predicted value, we need to find the difference between those two values, and that difference is known as an error. So error is the difference between the target value and predicted value, and every time the target value will be different from the predicted value, you need to calculate the error. So the concept of error is that error is the difference between target and the predicted value. If both values are equal, the error is 0. And if the error of your linear model is 0, it means your model is 100% accurate. Otherwise, you have to calculate error for those samples where the target and the predicted values are not equal. If we see this sample, for this sample, the error is 0 and the error is also 0 for this sample. But for the rest of the sample, there is an error, whether it is a small error or a large error, and we need to calculate that error. So in this lecture, we learn about the target value and the predicted value. We see that when those values are equal, there is no error and the accuracy of model is 100%. On the other hand, we see that if the target value and the predicted values are not equal, then we have to find the error. So I hope you understood the concept of the target value and predicted value in this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in the previous lecture, we learned about the target values and the predicted values. We learned that when target values and predicted values are same, then there is no error, and that situation is called an ideal situation. But in real situation, there is always an error. There are target values and predicted values for some samples or many samples which are different from each other. In that case, we need to calculate the value of error. Look at this target value. So this target value is far away from its predicted value. In that case, we need to calculate the error. Also in this figure, there are many data points which are a bit away from their predicted value. So for all those data points, we need to calculate the error. So this is the way of calculating the error. We need to subtract the predicted value from the target value, or we can also subtract target value from the predicted value. So error is basically the difference between the target value and the predicted value. Now error has been calculated. What is the next step? So next step is that we want to reduce this error in order to improve the performance of the regression model. Now, how to improve the performance or how to reduce this error? So suppose if the target value is 5 and the predicted value is 10, so the difference is 5. So with this simple value of 5, I cannot do anything. I cannot apply any algorithm or some mathematical method in order to reduce the error. So in order to reduce the error, we need to transform this error into a function. So the function in which we transform our error is known as cost function or loss function or objective function. So there are three common names which are used in literature. You can call it cost function, loss function, or objective function. Now, how to transform this error into a loss function or a cost function? So this cost function or loss function is known as mean square error, or in short MSE. Now this is the way of transforming error into a mean square error, which is the cost function for our regression analysis. Now that is our predicted value and this is target value. If I subtract them, I will get the error. So this error term is here. Then we are squaring this error term to make it square error. And then we are taking the mean by adding all the error and divided by the total number of sample in a data set. So this error or this loss function is known as mean square error. So we move in the reverse direction. In mean square error, error is the last word. So we calculate the error first, that is the target value minus predicted value. Then the second last word is square. Then we do squaring on the error. And then the first word is mean. So we will do it at the end. That is, we will calculate the mean by sum of all the square error and then divided by the total number of sample. So this is our mean square error. And this is the same figure which we use to understand the concept of the error. So in this way, we have transformed our error into a loss function or a cost function of a regression. Now this is a loss function. Now there is a square on it. I can easily take the derivative or I can apply any other method in order to reduce this loss function. So we cannot reduce our error directly. So in order to reduce the error, we transform the error into a loss function. So for regression, our loss function is mean square error. Now we have to reduce this loss function. So how to reduce this loss function? So in order to reduce this loss function, we have to use a least square method. So least square method is a method which is used to reduce this loss function. So in the next lecture,
we will study how to use least square method to reduce the loss function of a regression. I will see you there in the next lecture. Hi everyone, welcome to this lecture. Now we have transformed our error into a loss function, which is a mean square error. Now the target is to reduce this loss function, and in this lecture we will learn how to reduce this loss function using least square method. Now student, why we reduce the loss function? So basically we reduce the loss function in order to reduce the error. When error is reduced, the performance of model is improved. Basically, when the model is improved or its performance is improved, it means we have adjusted the weight and bias of the model. So by minimizing the loss or by reducing the loss function, basically we are improving the model performance, or we are adjusting the weights and the bias of the model. So let's see how we can minimize this and how we can adjust the weight and bias of the model in order to get the improved performance from the model. So this is the least square method. So we define here least square method as a cost function or a loss function. And now we will reduce this loss function. So this is the step of a least square method, or here we have set up a least square problem. So you can see that it is a difference of y minus xw. Here y, x and w, these are all the matrices. So this least square method is set up in the form of matrices. Y is the matrix of target value, X is the matrix of feature, and W is the matrix of weight. So if we multiply X by W, we will get the predicted value. So basically, inside this norm, inside this double bracket, which is called the second norm of Y and XW, and we are squaring it, we have the difference between the actual value, which is the target value, and the predicted value. So this is the way of setting up a least square method. So this is a difference and we are squaring it. Now, how to set up a least square method on a particular data set? So this is our multiple linear regression data set, and we can see that we have two features here, x1 and x2. So this is our output or y value. Now, this is the output equation or the regression equation for multiple linear regression, where W0 is a bias and W1 and W2 are the weight associated with x1 and x2. Now, how to set up a least square problem from this multiple linear regression dataset? So basically, we have to create three matrices. We have to create Y matrix, we have to create X matrix, and we have to create W matrix. If we go back and see the equation of a least square, we need three matrices, Y, X, and W. So we will create these matrices from our dataset. So this is our data set. So how to create Y, X, and W? So this matrix will be Y. The matrix of a salary or the output variable or the dependent variable will be Y. The matrix of the features will be X, and the matrix of the weights will be W. So this is our Y, this is our X, and this is our W. Now we have to note the dimension or the sizes of these matrices. This is very important. Here we have 5 samples, therefore the size of Y matrix is 5 by 1. Now here we have 5 samples, but we have two features. If I go back and see, we have two features, x1 and x2. So these features are present in this X matrix, which is the matrix of feature. So it has two columns and 5 samples, so its size is 5 by 2. It has only two values in the row. So there are two rows and one column. So this is our weight matrix. Since we have two features, therefore we have two weights. Now we know that in least square method, we have to multiply X and W. If we go back and see, we have to multiply X and W in order to get the predicted value. So in order to perform the multiplication, the column of X matrix should be equal to the row of W matrix. That is, we have two columns here and we have two rows here. It means now here the multiplication is possible and the condition for the multiplication of X and W is valid. Now this is Y, X, and W, three matrices for a small data set having only 5 samples. Let's transform this into a general equation. Suppose we have n number of samples. Rather than 5, we have n number of samples and we have d features. So in that case, this is the size or the dimension of y, x, and w. Now y will be n by 1. Previously, it was 5 by 1 because we had 5 samples. Now we have n sample, so the size of y is n by 1. Previously, the size of x was 5 by 2 because we had 2 features. Now we have n samples and we have d feature. Therefore, the size of x is n by d. Previously, the size of this W matrix was 2 by 1 because we had 2 weights with the features. Now we have d features. Therefore, we have d weights from W1 to WD. Therefore, the size is d by 1. Now, if I see the size of x and w, the multiplication is still valid because x matrix has d column, whereas the w matrix has d rows. So the condition of multiplication is still valid. Now there is problem here. The problem is this is the matrix of weight, but there is no bias inside this weight matrix. So if I add bias here, then the dimension of this matrix will change. Look at here. Now, if I add a bias term in the matrix of a W or the matrix of a weight, now its dimension will be changed from D by 1 to D plus 1 by 1. So previously it was D by 1. When I insert a value of a bias in this matrix, its size becomes D plus 1 by 1. Now it becomes D plus 1 by 1. So if it is D plus 1 by 1, then in order to multiply it with X, we have to transform this D into D plus 1 as well. So how to do this? So basically, in order to transform D into D plus 1, so that we can always perform the multiplication of X matrix and W matrix, I have to append 1 in the first column of X. You see, previously this 1 was not present in the feature matrix. Now I have append 1 at the first column of this matrix. Now the 1 column has been added. So the dimension of column of this matrix has increased from D to D plus 1. So when we insert the value of the bias, in that case, the dimension increases, and in order to keep the multiplication valid between X and W, we have to append 1 at the first column of the feature matrix. Now the problem has solved. We have insert the value of bias and we have set the dimension size which are valid for the multiplication of X and W. So before going further, let's understand what is the shape of our least square function. So this is our least square function. It is a square function. So it has convex shape. Look at this shape. This shape is a convex shape. Now, what is the advantage of convex shape? Basically, we want to minimize this value. So the advantage is in a convex shape, we have only one minimum value, which is at the bottom of the function. Now, if I want to reach at this point, I have to take the slope of this function. This is the point in the function where the slope is 0. And this line has a slope, this line has a slope, but at this point, the slope is 0. So in order to find the minimum value, which is my target, because I am going to reduce the error, I am going to find the minimum value of error, or I am going to find the minimum value of my loss function. So for this, I have to reach here. In order to reach here, I will take the slope of this equation and put it equals to 0. When I will take the slope and put it equals to 0, I will be at this point, which is the minimum point, and then my problem will be solved. So in order to go further in the mathematics, it was important to get the concept of a least square function. That least square function is a convex function, and the advantage of convex function is there is always one minimum value, and that value can easily be obtained by taking the slope of the loss function and put it equals to 0. So this is the step which we are going to do. Let's calculate the slope of this least square function and put it equals to 0. So this is our least square function. Now the next step is we want to expand this into 2 brackets. Now this is a square. If I want to expand it, this is basically the dot product of 2 brackets. That is y minus xw transpose and y minus xw. So here is the expansion. Now we want further expansion. We want to open these 2 brackets. So it will be open like a minus b whole square. So this is our a, this is our b. So this is a square plus b square minus 2a and b. So here we have opened this according to the famous algebraic equation a minus b whole square. So a square b square minus 2ab. Now here there is also a square. Now we need to expand this term as well in the similar way as we expanded this. So this square will also be the product of xw transpose and xw. Now we assign this transpose to each value inside the bracket. So it will become w transpose and x transpose. And this is our xw. The next step is to arrange the term. Now we will move this w close to this w transform. So here we have moved w close to w transform, and here we have xt and x, and there is no change in these first two terms. Now we have w transpose and w. If I multiply these two, I will get w square. So we have reached to the expansion form of our least square function, and here is our loss. Now it's time to take a derivative. By taking a derivative, basically we are calculating the slope. And we have learned in the pictorial view of a loss function that it is a convex function. And in order to reach the minimum value of a convex function, we need to take the slope and put it equals to 0. So in order to calculate the slope, what we are going to do, basically we are differentiating this equation with respect to w and set it equals to 0 to find the minimum value. Now take the derivative with respect to w. So this term doesn't has any w. It will be considered as a constant for differentiation. Therefore, it will be equals to 0. So we will remove this. So this is term which contains w. So the derivative of this term will be 2xty. Similarly, this is w square. So the derivative of w square will be 2w, and xt and x are there. Now here we are putting this equals to 0 in order to find the slope or a minimum value. Now in order to simplify, we dividing this equation by 2. Just divide this equation by 2. So 2 will be removed and we are left with x transpose y plus wx transpose x is equals to 0. So this is negative term. We will move this negative term to the right side of the equation. Now student, target is to find the optimal weight. As I told you at the start of this lecture that we want to reduce the error or we want to reduce the cost function. So why we want to reduce the cost function? Basically, we want to reduce the cost function to improve the performance of the model. And the performance of the model depends upon the value of the weights and the value of the bias. So basically, if the loss function is reduced and model has achieved its maximum performance, it means we need to calculate the new set of weights, or we need to calculate the optimal set of weights and bias. So if I want to calculate the optimal values of weight and bias, I need to move xt and x towards right side. So when I move these, since these are matrices, by moving from left to right, we have to calculate the inverse. So this is the final form of least square. So we know that whenever a data set is given, we have x and we have y. We only need x and y in order to get the optimal value of the weight. So student, this is the least square solution. In this solution, we have the minimized value of the error, and the weights and the bias obtained by using this method are the optimal values of the weight and bias. So in this lecture, we learn how we use least square method in order to reduce the value of the cost function. We want to reduce the value of the cost function because we want to reduce the error. We want to reduce the error because we want to get the maximum performance or the optimal performance from the regression model. Since regression model is a machine learning model, so the performance of regression model will be improved if we adjust the weight values and the bias values of the model. So everything about the performance of regression model depends upon the value of the weight. If the model is not performing well, it means we need to adjust the value of its weight and bias, or we need to find the new or the optimal value of the weights and the bias of the regression model. So we have found the optimal value of the weights and bias of the regression model using this least square method. So in this lecture, we learn how regression is performed using least square method, how the cost function is reduced using least square method, or how least square method is used to find the optimal value of the weights and bias. So when you solve this value, you will get the optimal value of the bias and the weights of a regression model. So that values of the bias and the weights are called the optimal value, and those values will representative of the best regression model. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture. Hi everyone, welcome to this lecture. So in this lecture, we will solve a numerical example on least square method. So this is the dataset which I have selected in order to solve a numerical example on least square method. So this is the simplest form of a dataset where we have only two samples and we have one feature which is experience in years and our target value which is salary in dollar. So we have two samples for this dataset. Now we know that in order to implement least square method or in order to solve a problem using a least square regression, we need to construct three matrices. That is Y matrix, X matrix, and W matrix. So Y matrix is the matrix of target variable. So my matrix will be obtained from this column. So it has two values, 30,000 and 50,000. Next, we have a feature matrix. So we have only one feature. The values are 3 and 5. So these two values are at the second column of X. Then we have only one weight because we have one feature and we have one bias. So this is our weight or W matrix. Now, in order to multiply X and W, the condition is that the number of column in X matrix should be equals to the number of rows in W matrix. Now, W matrix has two rows. So we have to create another column in X matrix. So we need to append one at the first column of our feature matrix. So we have also seen this step during the derivation of least square regression, that in order to keep the multiplication possible between X and W, we need to append one at the first column of the feature matrix. Now everything is set, it's time to apply least square method. So the first step in least square method is to take the transpose of X matrix. So this is our X matrix. Now the transpose of X matrix is here. In transpose, we transform the rows into column. The first row is 1:3. So we have transformed it into a column. Similarly, we transform the second row into a column. So in this way, we have an X transpose. Now the next step is to multiply X with X transpose. Here we are performing the multiplication of X transpose and X. So this is my X transpose matrix and this is my X. So the size is 2 by 2. Therefore, we can easily multiply both these two matrices. So when we multiply X transpose time into X, we will get this matrix. So basically this one will multiply by this one. Then this will be multiplied by this. And then we have to add. That's why 1 time 1 is 1. 1 time 1 is 1. And when we add, we will get 2. Similarly, this one will multiply with 3, and then this one will multiply by 5. Then we will add them and we will get 84. So similarly, the multiplication of X transpose and X will result into this matrix. So next step is to take the inverse of this matrix. If we take the inverse of this matrix, so this is a very simple matrix, just 2 by 2. If we take the inverse, we will get this value. So we have completed the calculation of this part, that is X transpose time X. And finally, we have taken the inverse of this product. Now, the next step is to multiply X transpose into Y. So the next step is X transpose into Y. This is my X transpose and this is my Y matrix. So the size of this matrix is 2 by 2. So this matrix has two columns and this matrix has two rows. Therefore, the multiplication is possible. So after multiplication, we will get this result. Now, the last step is to multiply X transpose X inverse and X transpose into Y. So we have to multiply these two matrices. So we have already calculated this matrix, which is here, and we have already calculated this matrix X transpose times Y. And now this matrix is here. If we multiply these two matrices, the multiplication is possible because the number of columns in this matrix are 2 and number of rows in this matrix is 2. So this will multiply with this term and then this will multiply with this and finally we will add them. And similarly, this minus 2 will multiply with 80,000 and 0.5 will multiply with 340,000 and we will get this value. So this is our least square solution of a data set which we have selected for this particular problem. We can see that the bias value is 0 and the weight is 10,000. So in this lecture, we learn how to implement least square regression. We select a numerical method in order to understand all the steps of a least square regression. We see that we have obtained the optimal value of the weight, which is 10,000, and the value of bias is 0 for this particular example. So this is the optimal value of weight and bias. and these weights and bias represent the best regression model on this dataset. So I hope you understood this lecture. Thanks for listening, and I will see you in the next lecture.